In the last lesson, we learned that a great way to calculate heat exchange is Q equals mc delta T. And a little refresher, we learned last time that C stands for heat capacity. That's right. And the Q stands for heat. M is mass, and so we were able to use it to interrelate the amount of the change in temperature we saw with how much heat we either put in or took out. And so in this lesson, we're going to turn our attention to the heat capacity of metals. So maybe we'll do a stovetop demonstration here with metals. But that's our goal here, is to be able to calculate heat exchange with metals. Now, of course, it's not going to be any different than we did with water, but it's going to let us explore the idea of heat capacity a little bit more now that we have more than one substance. So let's look at this. I'm going to spend a fair amount of time being pretty precise about this. Let me make sure the sound is down. If we have 93.3-ish grams of this copper metal, that's copper metal, I'm going to weigh out pretty much as close as I can to the exact same mass of water. Because we know if we're going to do any comparisons, we probably need to have the exact same mass. So let's see how close I can get it. All right, so that's pretty darn close. Exact same amounts of each one. We're going to take these two and we're going to put them back on my stove, pretty much equidistant from the center of the burner, assuming that they will absorb the same amount of heat. So what I want you to do is I want you to make a prediction. If they start at the same temperature, which is roughly room temperature, although you notice it was pretty cold in my house that day. The only difference between these two thermometers, I think, is just calibration. So assuming they're starting at the same temperature, which one of these two will have the larger change in temperature, assuming that they're absorbing the same amount of heat from the burner? Well, let's see. Let's see what happens here. I believe it's time-lapse, so it should speed up pretty quickly here soon. Still a little bit close. All right, there you go. I think I see it. There's definitely a larger change in temperature of that metal versus the water, despite that they have the fact that they have the same amount of material. So why is that? Well, it's because they don't have the same heat capacity, right? So what do you think? Does that mean the metal has a higher or lower heat capacity than the water? Well, if we look at a heat capacity table, and remembering the definition of heat capacity, it's the amount of heat energy in joules needed to raise the temperature of 1 gram of material by 1 degree Celsius. Well, if you look at a specific heat table, and this one doesn't have units, which is kind of sad, and you look at water here, what it's saying is that water requires you to enter 4 joules of energy to lift the temperature of 1 gram of water by 1 degree Celsius. But look at copper. Copper only requires, 10 times less energy in joules to lift its 1 gram by 1 degree Celsius. So you can see it takes way less energy to change the temperature of the copper, and that's why we're seeing this bigger change in temperature. I'm assuming they're getting the same amount of heat. You could argue that, I think. But definitely because of the smaller heat capacity, you're seeing a much bigger change in temperature. Look at these cool things here. So I found on this, people collect coins, and I found on this site they were talking about these are all apparently exactly 1 gram samples of these. Now, I'm a little suspicious because they look like they're about the same size, and I honestly would expect some to be slightly larger, and maybe they're different thicknesses or something. I don't know. In any case, I have this lovely heat capacity table over here, and what I want you to do is I want you to make a prediction of the metals I have here. Let's not do these two. Of the metals I have here, which are largely represented there, which one of these would see the, let's go with smallest change in temperature, assuming you heated them all the same? Well, the one with the smallest change in temperature is going to require a lot of heat to change its temperature, even a small amount. So if you look at iron, iron requires 0.4 joules to change its temperature 1 degree Celsius, and so therefore it should see the smallest change in temperature. I'm not including these two. Yeah, and I would expect gold to see a very large change in temperature and lead to see a very large change in temperature. So iron would be the smallest change in temperature of them all. All right, so pretty simple, and we know that if we were to put calculate the amount of heat absorbed by that copper, it'd be pretty darn simple, right? We'd be using the exact same formula we did here. Our change in temperature would be final minus initial. We'd pick out our specific heat from this table, and we just need to know the mass is 93.30. So here we go. So Q equals 93.30. There's my specific heat. Just got to make sure I have the right one this time, and I have to make sure my units cancel, right? One of the reasons that you should put units on a specific heat is because you want to make sure your units cancel and you're not being tricked by anything. And I would get this many joules, not including sig figs. All right, so here's what I want you to do here, just to kind of get to what we're thinking about sig figs a little bit. I did not round it to sig figs, but I want to know, to improve the precision of this measurement, would it be better to invest in a better balance, or would it be better to invest in a better thermometer? And why? Well, if you said the answer is invest in a better thermometer, you are correct. We are getting 4 sig figs from this cheap little balance. And we are only getting, you might think 3 sig figs here. Yeah, when you subtract them, you're definitely still going to get 3 sig figs. You remember, sometimes in subtracting, like if this was like 80 and that was 79, right, you'd get down to 1 sig fig pretty quickly. But it was a 3 sig fig measurement here, and so it wouldn't do us any good to improve the balance. We need to improve the thermometer. All right, so since we understand this, we've practiced this a lot. What I want to know is if you wanted to melt these iron nails in the same way they've melted all of this molten iron over here, what I want to know is, given this specific heat table, let's move me, that's not useful. I want to know if iron melts at 1538 degrees Celsius, if you wanted to melt 10 grams of iron nails, how many kilojoules of heat would be required? Well, here's what I got. I said I've got 10 grams. I know that my specific heat is in joules per gram degree Celsius, so there's no trick there. I don't need to switch my units there. This is degrees Celsius. Those will cancel, and I'll be left with joules. And I hopefully chose the right, I chose the right specific heat. I get 6,808. However, the answer they wanted was in kilojoules, so that's 6.808. And I'm rounding it to 1 sig fig because sadly, you know I wrote this problem because I am not a type A person, and I had 1 sig fig there. A little reminder of sig figs. I know this is the correct answer. If ever your specific heat is limiting your sig figs, you don't want to let it do that. In other words, typically you would look one up with more digits. So never use this as your guide for a number of significant figures. You always want to use your measured values because you could always look up a more accurate specific heat. Okay, so we've got this aluminum bar over here. What I want to know is what would be the final temperature of that aluminum bar if you heated 200 grams of it. Ooh, it's small. It looks big here. 200 grams, it's not going to be very big. Of this aluminum with this much heat energy, and you start at 25 degrees Celsius. Well, I got about 45 degrees or so. Why? Well, first of all, I solved for delta T by doing Q over MC, plugged in my values. I checked, because I know specific heat is in joules per gram degree Celsius, that my units canceled. I'm not being tricked here. Yep, grams. Grams don't have to do any unit conversions. And when I calculate that out, that gives me my delta T. I dropped it to 1 sig fig because our mass is only 1 sig fig, so about 20. And of course, that's not the answer because it said what is the final temperature, and we started at 25, so we have to add that to it. It's going to be about 45, and you know, that's not a significant digit, so you could argue, really honestly, it's about roughly 50 degrees Celsius. All right, very good. Now, one last thing that I want you to think about here, and this sort of gets to, do you understand the idea today of what's going on? I will tell you, this question I'm about to ask you is not as simple as it sounds. A little trick to it. So I'm about to take these two metals, copper and aluminum, and strap them to my stove. You see they're about the same temperature. Only difference is because of the calibration of the thermometers. I'm going to strap them to my stove. I'm going to turn that burner on the back, and I want to know which would see the bigger change in temperature. Okay, let's see what actually happens here, and then we'll see if we can try to explain it. I think it's going to be time-lapsed. I'm hoping it's going to be time-lapsed. There we go. Let's get the stove going. Oh, it's pretty close. Oop. All right, so let's look here at the end. It was really, really close, but definitely the aluminum had a bigger change in temperature. Now that should be a little bit of surprise here, because think about this for a second, right? Aluminum has a larger heat capacity. It should require more heat energy to lift it 1 degree Celsius than it should copper, but why are we seeing a bigger change in temperature? Well, it's because specific heat was not the only factor here. These two lugs of metal here look similar volume, but that doesn't mean that they're the same mass. So they had different masses, and that's why we saw what we saw. So aluminum, if they were the same mass, would have had a smaller change in temperature than copper would have, given equal masses, right? But they didn't have equal masses, and I suspect that the copper had way more mass, and because it had way more mass, it would require way more heat to see that change in temperature. So this is my reminder that it's not just the specific heat that determines how much change in temperature you have, it's also the mass. Those two things play a very important role.